Hi, my name is Kaushik Roy from the AI Institute at South Carolina, and today I will be presenting our work on top semantics, down syntactic language representations. So roughly what this idea means is that we figure out for a particular set of tasks the kind of semantics that we want the model to encode. And we go about infusing those semantics in the key parametric structures of the model systematically. So what do I mean by that? So the parameters that govern the semantics that a transformer model learns is the attention matrix. So essentially, what that matrix learns is that if between tokens in language, how much do they co-occur in what context? So what I mean by that is consider the token war. It might co-occur frequently in various contexts with the word civil or with the word proxy or with the word Iraq, for example. But it may seldom occur with the word great. That may be due to various reasons. One such reason may be that the Great War is more commonly referred to nowadays as the First World War, and you may not find many articles that refer to it as Great War and the language model corpus that it is trained on may also not contain many mentions of it. So if we are looking for specific semantics of this nature that we want the model to quickly capture, we can use our method to do so. So the way we achieve that is that we construct an attention mask and apply that mask, and we get a modified attention matrix that consists of co-occurrence probabilities that encode the necessary semantics. So it's a simple idea, but a powerful one. So when we do this, we see drastic improvements over even large models. And we'll come to the reasons for that in a bit. So here we see a depiction of how any transformer model, for example, BERT, can be taken and TDLR can be applied by simply applying the attention mask to the attention matrix and then letting the rest of the fine-tuning layers learn the parameters as normal. So here we can see that TDLR, even the base model, achieves better performance than the large models of BERT on domains, several domains from the GLUE benchmark. The reason for this may be that these data sets, they require external knowledge, so not contained in the words themselves, but are contained in external sources. So for these experiments, we specifically use the knowledge graphs ConceptNet and WordNet to form our attention masks. So to tell between the two types of world war, sometimes the words themselves may not be enough. You may need additional information about the war, such as the technology used at the time, the kind of warfare carried out, such as chemical weapons and trenches versus planes and tanks later on, or the perpetrators, etc. So by leveraging that kind of common sense knowledge and the fact that war may contain synonyms like conflict from WordNet, we achieve better knowledge capture using TDLR. So one might think that this operation appears arbitrary, but it's really not. You can see it as Bayesian posterior modification, where the mask can be thought of as a strong prior. And so that also explains why the model converges faster with even the base model over the large models, because with trillions of parameters, there is plenty of degrees of freedom, and TDLR quickly captures the required semantics, even in the presence of so many degrees of freedom. So we presented a novel method to infuse specific semantics into the self-attention mechanism of any transformer, but we have chosen BERT for experiments. In future work, we will explore factual knowledge, for example, as necessary in question answering systems, or even more specific domain knowledge as may be necessary in medical application systems. Thank you.